It's as simple as something that nobody knows it. Her eyes are as big as her bubbly toes on the feet of a queen of the hearts of the cards, and her feet are all covered with tar balls and scars. It's a common something that nobody knows it. Her beauty will follow wherever she goes, up the hill in the back of her house in the wood. She loved me forever, I know she could. I remember when you and me.
All right. Hopefully everything is all set up. We're going to continue with Chapter 21, Section 2, Electric Circuits. So we learned some circuit diagrams or some circuit components, symbols and schematics. So we're going to take a look at two basic types of circuits, the series circuit and the parallel circuit, and see how they're different. A series circuit is just components daisy chained together in a series. Parallel is where you have the branch, the circuit branches. So in a series circuit, there's no branching. So if you have your power source here with a certain voltage, you'll have your wires connected to, say, one resistor up here, and then another resistor over here, and then say a third resistor over here, and they're all in a line. They're all in a chain, right? There's no branching. The current has to flow through all of the components, and it has no way of taking another path. And the total resistance in a circuit like this is simply the sum of all the resistances in the circuit. So R1 plus R2 plus R3. That is different than a parallel circuit. In a parallel circuit, you have your power source, just like a series. Then you have a branching. So maybe right here would be a split, where some of the current can go here and some of the current can go there. Well, which direction is the current going? Again, current flow. So this is negative, or this is positive. So current flows in the opposite direction as electrons flow. Electrons are going to flow away from the negative toward the positive. So if electrons flow there, current's going to flow this way. So you can the current can move off into two branches here. And let's say there's a resistor here, and then it connects back with the circuit. And there's this other branch of the circuit with a second resistor that connects and rejoins the current. Otherwise, current couldn't flow at all if it didn't rejoin the circuit. And then the third branch there. So maybe resistance 1, resistance 2, resistance 3. And so current's flowing. Current has choice, right? But it doesn't technically have a choice, but let's not get into that. In a parallel circuit, branching is the key feature of a parallel circuit. And the total resistance in this circuit is actually given by this formula. 1 divided by the total resistance is 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. It's the reciprocal version, so to speak, of the total resistance in a series circuit. So these two formulas are going to be ones you want to know for this chapter. You can solve for the total resistance in a parallel circuit just by taking the reciprocal of both sides, right? And then you would have 1 over R1 plus 1 over R2 plus 1 over R3. So the thing is, interesting thing is that as you add resistors in a series circuit, the total resistance increases. So adding more resistors the circuit's total resistance increases in a series circuit. It's kind of opposite in a parallel. In a parallel circuit, adding more resistors in parallel, decreases the total resistance. So they have to be added in parallel, though, because if you add them in series, it's just going to add to that resistance of the series circuit. So you can have mixed series and parallel circuits, of course, right? We could put two resistors, we could put another resistor here or another resistor there. And so you've got these combinations of parallel and series circuits. We'll talk about those. Ohm's law, which we learned in the last section, Ohm's law, which is our V equals IR, can be applied between any 2 points on the circuit. We apply between any 2 points. You get to pick on the circuit. So with that principle, that allows us to do some circuit analysis. So let's look at what a short circuit is. Let's draw a diagram with. So we have our power source here. It's showing current going from, I wonder if I had that backwards. Is this, I've been saying this is the negative and that's the positive. I hope I didn't get that mixed up here. Let's do a little check. Google, keep me in line. I just dropped circuit diagram. My pen rolled down and then down again and then down again. And now it's falling all the way down to the ground. Okay. Ergonomics are not ideal here. Circuit diagram, power source, DC symbol. That should do it. Let's see what we have here. So this is the one we're looking at. Although that one has multiple, but that's okay. Here, battery. But it doesn't say which is positive. There, positive, negative. I did have it backwards. Oh, I'm so sorry. These positive and negatives sometimes. All right. Well, if that's the positive terminal, that's the negative terminal. So the longer one would be positive. The shorter one would be negative, which means the current would be going in which direction? Electrons would be moving in this direction, so current would be in the opposite direction. So current's going clockwise. All right. So I better fix my notes on that one. Apologize. Right when I introduced it. Now I have to check to see if the book is wrong on that. It's possible. Let's look at the book. Chapter 21, section 1. See, this is all part of learning, right? Verifying. I have a feeling it was me that was wrong. The book is fine. Where are these symbols? Does the book even have them? Okay, figure 21.3, it's right. Yep, that was me. All right. I don't think it has a summary like I did in my notes, but it does show you. Oh, there it is. No, on page 21.1. Yeah, okay. Well, my notes are fixed now. Okay, back to this particular circuit. Let's fix this here. All right, positive terminal, negative terminal. Current going clockwise. So in this particular circuit, we have a resistor here. It is a parallel circuit. And we've got a straight conductor there. Here we have a resistor there. And there we have a resistor here. Let's see. Oh. Kind of looking at that. This resistor isn't really, I mean, okay, every wire has resistance. There's some resistance associated with every wire. In this particular case, we're looking at a short circuit here. So we're trying to draw a diagram for a short circuit. A basic circuit diagram for short circuit would mean that you basically have one path where the resistance is essentially zero or very, very little. And so the current can flow through this first branch with a resistance of very close to zero. And then it can go back to the battery. It does not have to flow through resistance, resistor 1 or resistor 2. And so it's going to take, current will always take the path of least resistance. So you're not going to have any current through here. The current through resistor 1 would be 0, so I1. And current through resistor 2 would be 0, so I2 would be 0. All the current would be going through this first branch here. So all the current's going to be, this circuit is short-circuited. So if you had a light bulb or a refrigerator or some other motor or electrical device that you wanted to operate on these other two branches, they're not going to get any power because there's a short circuit, and all the power is going to be, all the electricity is going to be running through that no resistance or low resistance branch. Let's start a new layer. I didn't realize I wasn't at the top there. All right, so this is example 21.7. In the circuit shown in the diagram, the electromotive force, the EMF, is 12 volts. And each resistor has a resistance, and each resistor has a resistance of 450 ohms. We want to find the current supplied by the battery to the circuit. If there was no resistance, the current would be basically as much as the battery could put out. But because there are resistances, that's going to limit the current flowing through this circuit. What does the circuit look like? So we've got a power source. And that's the positive terminal. There's the negative terminal. So current is going to be going in what direction? Right, clockwise. Good. And then on the upper branch, or on the upper part of the series circuit, it branches into a parallel. So we have one branch with a resistor here, and then a branch with two resistances there. So the current can, pick the top branch, or it can pick the bottom branch. It can go through either branch. The amount of current flowing through each is going to depend on the resistances. So this is a 12-volt power source. All the resistances in this case are the same. So let's analyze this. So our EMF is 12 volts. Our resistances are all 450 ohms. We want to find the current I flowing through the circuit. So we need to essentially use both rules. This is a combination series and parallel. If you take this point here and this point here, it's as if this circuit element is in series with the battery, but that circuit element itself is a parallel circuit. So we need to find the total resistance of the parallel circuit. So we're going to basically we're going to reduce the circuit diagram to look, instead of we'll reduce it in two stages. Okay, first we're going to combine, maybe use a different color. We're going to combine these two into one resistance. Because these are in series, we can then draw our circuit as a parallel with only two resistors, where this resistance here, R1, is going to be given by the total resistance in a series circuit. So that's R plus R, or 2R. The resistance here is just R, as it is up here. So now what we're going to do, since we have R1 equal to 2R, we can now take this circuit and reduce it to a series circuit. Same power source here. But now we're going to represent that branching parallel bit, this part here, as one circuit element in a series circuit. So that whole thing we're going to represent with just one resistor. So this we'll call R2. And the rules are the total resistance in parallel is, well, if you recall, it's a reciprocal function. 1 over R2 is going to be 1 over R plus 1 over R1. All right, so that's 1 over R plus 1 over 2R, which we could say is 2 over 2R plus 1 over 2R, which is 3 over 2R. So that's 1 over R2. So what is R2? Take the reciprocal of both sides. So R2 is 2/3 R. So if R2 here is 2/3 R, we've reduced the circuit now to one series circuit with one resistance. So that resistance is going to be the total resistance. And now we're going to apply Ohm's law for the total circuit. We want the total current through the circuit. We have the total resistance, R2. This is R total. So we're going to use Ohm's law. When we apply Ohm's law, I'll do this to the whole circuit, we use V equals IR, but we use V for the total circuit, so that's 12 volts. The current for the total circuit, that's what we want to solve for. And the resistance for the total circuit, which is R2. So I is going to be 12 volts over R2, or R total. Maybe I should say R total, which is 12 over 2/3 of R. So that's 12 volts over 2/3 times 450 ohms. And that works out to 0.040 amps. So this is the total current through the circuit. So this is total, writing subscripts there. Let's see here. All right, let's look at some devices for measuring current and voltage in electric circuits. A common device is called a multimeter, and it measures voltage, current, and resistance. And I recommend that everyone have one of these in their toolkit because they can be extremely useful for troubleshooting household electronics. A multimeter measures voltage, current, and resistance. Don't mind the chatter in the background. Okay, oops, voltmeter, ammeter, voltmeter. There we go. So an ammeter measures current in amps or milliamps or whatever other units of amps. Current is measured but the difference when you're connecting a multimeter to a circuit to measure current, you have to connect it in series. So current is measured by connecting the ammeter. I don't know why they leave out the P amp meter, ammeter, in series with the circuit. So if you have a circuit and you're going to read the current through the circuit, you need to connect the ammeter in series, meaning in line with the circuit. So maybe here somewhere, you put your ammeter in here and you read the current. Here's a little needle with a gauge indicating your current. We'll draw it in a box. However, when you're measuring voltage with the voltmeter, voltage is measured by connecting the voltmeter in parallel to the circuit. In parallel. Oops, I think I did 2 R's. That's 1 R with the circuit. So if you have your circuit here and you want to read the voltage across a component, then you have to put one terminal of the voltmeter, maybe with an alligator clip, let's say, on one side of the component, and then the other on the other side of the component, and then you can read the voltage. And the needle will go up or down based on how many volts. This is here you're reading amperage. So those are the two main differences in measuring amperage and voltage. With regard to measuring resistance, you can't do so in a circuit, but you can do so across a component that is not inside of a circuit. So, we can calculate resistance though using Ohm's law. Oops, I didn't use the top part of the board. All right. that's actually all for section 2. So I'm going to stop here, and section 3 I'll make a different its own video. All right, thanks guys.